So I will not talk about any kind of signature thing, and I will not talk about spectral gaps. I will talk about a different way to approach kind of these the problems that Tali mentioned in her last talk, that topological expansion, or somehow the topological overlap property. And surrounding this are several conjectures that somehow I want to discuss, and somehow that will follow from that implied by the main theorem that somehow I will write down at the end. And the first conjecture is kind of a very innocent one. It's due to Grünbaum, and then Kalai and Zakaria had some contribution to this. And it states that, okay, so you look at the simplicial complex delta and you want to embed it into R2D. And you want to avoid all kinds of, first of all, let's avoid some topological nastiness, and let's assume that this embedding is in the PL category, okay? So we don't have all these nasty things that can happen in 4 dimensions, for instance, where things can be very, where embeddings can be very non-nice. So for the topologists among you, this is now I'm going to say that it's tame, if you want. And then you can ask, well, how many d-dimensional faces can you have in terms of d-1 dimensional faces? So usually the d-dimensional faces are denoted like this. So fd of delta, right? And then you want to ask, well, how many can you have? And clearly, if you just have all of them, then you see that somehow there will be some non-trivial intersections between these d-dimensional faces. So you cannot have all of them. So, but how many can you have? What's the best known bound that existed behaved roughly like this. So fd minus 1 of delta times f0 of delta times 1 minus 1 over 3 to the d. And this is due to Tamal Day. And then somehow various people tried to improve this, but usually they were just able to improve the constant here. So there was some constant here, they improved the constant. And then recently there was a student of Herbert Edelsbrunner that improved this to d-1 here. So 1 minus 1 divided by 3 to the d-1. And but the examples that people constructed, they weren't much smart. They were essentially just linear in fd-1, and indeed that is the right answer. So what we will prove today, or we will see a glimpse of today, is the following bound. It's this.
Sorry, what do you mean by this mapping of the complex to R? So what is the?
It's just an embedding. Embedding just means it's a continuous map that doesn't have any self-intersection. It's injective. Okay.
And what property do you want about the simplicity? So should they?
Okay, so this is let's say the map is piecewise linear. That's a good property to have. Okay. A similar problem was goes back to 4 to 5 authors. So Newborn was kind of a different paper. It's related, and I'm not actually going to start to say the names because I'm for sure offending someone. But the question is: so you have a complex gamma into that you map into R2D, and this is not an embedding. And in fact, you want to say that the number of D faces is large compared to the number of d-1 faces. And then what you want to say is that there are many intersections, right? So the many of the d-dimensional faces should intersect, and in fact they do. So the bound that you get is, so the number of pairwise intersection of d faces is called sometimes the d-dimensional crossing number of delta. And the bound that we will get here is fd to the d plus 2 divided by d plus 3 to the d plus 2 times fd minus 1 to the d plus 1. And you can see easily that this is essentially optimum of gamma, always. And
wait, what's the assumption on the embedding over there?
there's no embedding. This is just a map, okay? So this is otherwise the crossing number doesn't make sense. Okay, you see from the bound over there that you have to have non-trivial intersections. Let's say if the number of d faces is at least d plus 3 times the number of d minus 1 faces. And then exactly, so the point is that you have not only you have few intersections, you have actually many of them. That's the kind of the statement here. Okay, and the only assumption I again make is that I'm in a PL category. And here this is a kind of classical problem, colorability. So you want to determine the genus of a graph, right? The genus of the complete graph. In other words, it's the smallest, the least genus surface that the complete graph embeds in, and this you can also formulate as a conjecture, and we will also see that this is indeed something that you can prove directly. So what we will see is that if you take the k-dimensional complete, the k-dimensional simplex on n vertices, and you take its k-skeleton, and it embeds into a manifold, let's say with kth Betti number defined as follows. Then we have that this n minus, so the number of vertices minus k minus 1, choose k plus 1, is bounded from above by 2k plus 1, choose k times the kth Betti number. And all these theorems were known usually in the case when d equals 1. So when you were embedding graphs into surfaces, right, into two-dimensional surfaces. So this is here, for me, this is a manifold of dimension 2k. So for k equals 1, this is exactly embedding of a graph into a surface, and you're asking what is the maximal number of vertices of a complete graph that you can embed into a surface of a given genus. And this question here, well, okay, so what is it? So this is a graph into the plane, and then you can get from Euler's formula that the number of edges for a planar graph is at most 3 times the number of vertices. And this is kind of the natural generalization of this to higher dimensions. And similarly, this kind of crossing number lemma was known if you had graphs that you had in the plane. And some graphs that you map to the plane, and if they had too many edges, then there had to be many intersections. So this is a kind of, this in particular is a kind of property that Tali was also alluding to. So if you want to have, usually Tali says, okay, so if you have some kind of spectral properties, then you want to say that there have to be many overlaps, and this weakens this assumption a little and says, okay, if you have only many faces, right? If there are small, globally the density, the number of faces is high, then you have to have many overlaps.
By the way, is that high dimensional thing sharp also? What's the manifold for which it's...
Which one? This one?
Yeah, because now when you're in high dimensions, you've got a lot of manifolds.
Well, you can just take the natural handle body construction, right? That's sharp. Okay, so it's also the sharp construction in dimension 2, but then there are not so many. Yeah. Right. So you can improve this. In particular, you could also replace this Betti number, which measures just the dimension of the rational homology, by any other homology, and then you would get another bound, and that's also true. And so in particular, it's not somehow for a given manifold, this may not be sharp. And then there is another conjecture that is kind of was kind of more sought after in the last years. It's called the G conjecture. And it has a kind of different flavor. So it's due to McMullen. And what he said is, okay, so what he takes is sigma triangulation of the d-1 sphere. And then he wants to characterize the possible number of faces that you can see. So in particular, what he wants to characterize is the number of vertices, the number of edges, the number of two-dimensional faces, and so on. And why am I writing them like this? Because he said, okay, so this vector here, you cannot see the characterization so well, but what you can do is you can do a kind of transformation to another vector. And what you do is, okay, so you do just an inverse Pascal triangle. So here's this entry is just the difference of this and this entry, which I just assume is 0. So this entry is the difference of this and this entry, so it's f1 minus f0. And then you fill this out, and then you get a vector here, h0, h1, to hd. And this vector hd, you can show is palindromic. And what McMullen then did was he took this Pascal triangle one more time. So and he just took it for the first half of these vectors, because the rest was determined from the first half. So he said, okay, so then you get to this vector g0, g1, and so on, up to d half. And now you have this nice vector, and he said that you started with the face vector of a sphere if and only if this vector g that you get here is of a certain nice form. So what he said is should be the, so
Face vector of a sphere means a triangulation.
yeah, it's a triangulated sphere, right? So he said that so f is a face vector of SD minus of sigma, if and only if this vector g is an M vector. And it's a little tricky to write down what this means in general, but you can just think of it as G vector is saying that somehow an M vector is saying that you are the Betti vector of a commutative graded algebra generated in degree 1. If you don't want to go over this too much, I mean, there is somehow it in particular says that the G vector is non-negative. It also says that the G vector cannot grow too fast. If you have so many elements in degree 1, then there can be no surprising elements appearing in degree 2. Right? It must be roughly quadratic of whatever you had in degree 1, and so on. And so this was the conjecture. And then there were some partial results towards this. So there was an implication. So if sigma is the boundary of a polytope, then Stanley proved that the G vector is indeed the associated G vector that you get is in fact an M vector. And then there was a kind of very cool and very miraculous construction by Bilera and Lee that if you have such, if you get somehow this, if you have this M vector down there, then you get a triangulated sphere, and in fact a simplicial polytope with that face vector. Okay, so that is what was known, and somehow the consequence of what we will discuss today is essentially that somehow that this is true for general triangulated spheres. So it's a kind of extension of Stanley's result to triangulated spheres. So how do we do this? And I want to kind of do this on the example of this theorem and somehow develop what is necessary to prove this theorem, and then somehow say this about how you get from the statement that you have in the end to the other theorems as well. So the Grimman-Saccaria conjecture, and I do this is not by accident, because this is some other conjecture that somehow essentially inspired their approach. So how do we attack this this conjecture? So we heard in Federico's talk of this algebra A that you can associate to a simplicial complex. And so he associated it only in the case of Bergman fans, of matroids. But we can do this for general simplicial complexes. So the way that you can do this is you look at just a polynomial ring where you identify the vertices of your polynomial ring with, the vertices of your simplicial complex with indeterminates. And now you look at a quotient, so you want to describe this, whatever simplicial complex you started with, let's say delta, you want to describe it better, so what you do is you mod out by an ideal I delta, which is defined by taking out the ideal generated by all the monomials whose support is not in delta. Okay, so this is a nice description. And it turns out that this is kind of, if you want, this is kind of a commutative version of the simplicial chain complex. Unfortunately, it's an infinite dimensional object. And now, what you want to do is, okay, so you want to, this is an infinite dimensional object and it's a vector space. So what you want to do is you just want to factor out a linear system of parameters. So you want to factor out enough linear forms so that it becomes finite dimensional. So usually A of delta is then defined as the quotient of R of, let me call this R of delta. This is R of delta modulo some system of linear forms, and I want to say that this is just enough linear forms to make this a finite dimensional vector space. So theta 1 to theta k, where k is the cool dimension. And in fact, you can show that the cool dimension, this is equal to
What's the cool dimension?
It's some of the minimal length of linear forms that you have to take out until this is a finite dimensional thing. Okay, so for simplicial complexes, you can just, this is just the cardinality of the maximal simplex, okay? So this is just the dimension of delta plus 1.
It's the maximal length of the chain of ideals, right?
Yeah, but, okay. I mean, there are various ways to think about this.
By the way, don't you need something about, to make it, to kind of my colleague, don't you need something about links there?
Yeah, I mean, but I'm not going to, I mean, for now, I didn't discuss Cohen-Macaulay. Actually, Cohen-Macaulay does not matter so much.
At all?
For this conjecture, I mean, there is no condition here on delta. Okay? So how do we get to this conjecture? Well, we start in kind of the same way that you prove the planar case. So the planar case works as follows. You take a graph that is planar and you extend it to a triangulation of the plane. And in the plane, you can do this in a miraculous way. Right? So if you have a graph that is planar, something like that, then you can always add edges until you have a triangulation of the plane. Right? In the monotone way, you don't have to add any vertices. For two complexes in R4, this is not possible. But you can always find a triangulation of the sphere that contains your complex as a subcomplex. Okay, so you start with delta, right? And you embed it into sigma. And sigma is a triangulation of a sphere. And now I want this to be, of course, so what would be the triangulation of the sphere? Well, it should be a 2D dimensional sphere, right? This is a sphere that I know that I can embed in. Right, so this is S2D. Okay, so what do I do now? So now I compute this ring, right? This ring A of sigma.
So when you do that, you don't add new vertices, or do you?
I have to add, sometimes I have to add new vertices. Okay?
You're not doing it optimally, right?
No, I do it anyway. And in fact, somehow the whole thing about this approach is that once you formulate this algebraically, it doesn't really matter how you do it. Okay, in fact, this is kind of one of the key features of what we do. So this is A sigma. And notice that A sigma, if I speak of this A sigma, it's not really well defined, right? I could have chosen various ways of finding these linear forms here. So this will be important. But now, for now, let's look at just A sigma. Okay, so A sigma is now a nice ring. It turns out that if I look at the dimension of A sigma in degree I, then this is exactly this number hi of sigma that I had in this triangle before that I just deleted. Right? So this is this number that appeared just above the G vector. All right, so the dimension of this, so in particular, this vector is so I said earlier that the vector is palindromic, and there's a reason for that, and this is that it is a Poincare duality algebra. So A of sigma is a Poincare duality algebra. Satisfies, so Federico just abbreviated this with PD yesterday, so let's just say it like that. So it satisfies Poincare duality. What do I mean by that? Well, okay, so we have this object in the 2D dimensional sphere, and this means that the top degree for this, the top non-trivial degree of this object is in degree 2D plus 1, 2D plus 1 of sigma. This is just a one-dimensional vector space. So this is just the reals. And okay, so there I can just write down this. I can just identify them using whatever map I like. It's kind of the map, this map DEG, or this degree map that we want sometimes to discuss. We just fix this map. And now what I mean by Poincare duality algebra, well, I want to say that if I look at something in degree k and something in degree 2d plus 1 minus k, right, then I can multiply these two objects. And what I get is an element in degree 2d plus 1, which I identified with the reals. And this pairing here, the statement is that the pairing is perfect. Okay, so pairing is perfect. So this pairing is perfect. In particular, this and this space have the same dimension as vector space.
So what does perfect mean?
It's a bilinear form. It's not degenerate. For every element here, you can find an element here such that you are non-zero here. And for every element here, you can find an element here that you're non-zero here. Okay, that's a perfect bilinear form, but not degenerate bilinear form. Okay.
So far, you didn't use anything about the embedding, right? Or did you?
I didn't use anything about the embedding, no.
Okay.
And now, how is this ring connected to the phase numbers? Right? I want to in the end I want to say something about the phase numbers. Well, it turns out that first of all, this ring is somehow in degree k is generated by the phases of cardinality k. So in particular of dimension k minus 1. So what I have is, let me already pass to the subcomplex. So let me say, okay, so what I will do now is a slight abuse of notation. So what was A of sigma? A of sigma was this polynomial ring of sigma modulo some linear system. And let me just define A of delta for me now, and then there's some cheating here, right? This is, and I will say what this is. This is just R of delta modulo the same linear system. Okay. This is a little cheating. Why? Because this is not the A of delta that I just defined, because the complex sigma here may be of a larger dimension than the complex delta. In particular, this here may be more linear forms than just the cool dimension. But okay, so we have to, this is fine. This is fine. It doesn't really matter for us.
If you add new vertices, you also have different variables.
Yeah, that's right.
So you sort of project the function?
Yeah, well, I mean, this is, okay, so this is a, right, this R of sigma naturally contains R of delta as a quotient. Right, in what way? Well, okay, so how do I obtain R of sigma? Well, I take out all the non-phases, right, and now I just take out more of these, right? Right, I take all the non-phases of delta. So there is a surjective map here. And then now we have this, with this notation, we have A of sigma, the surjective map onto A of delta, right? Just by definition. There's just nothing fancy here. Now, okay, so how is this related to the phase numbers? I said that somehow the k phases, the k-dimensional phases generate the degree k plus 1. How can I use this in any way? Well, I can use this to say that A of AD of delta, so the degree D component of this ring A of delta, well, this is as a vector space bounded in dimension from above by the number of d-dimensional faces. Well, not quite, sorry. It's degree D, so the d minus 1 cardinality D faces, so d minus 1 dimensional faces. Okay? This is a simple inequality. There's another simple inequality, right? So you can estimate the vector space by looking at the cardinality of a generating set. The other way to say to estimate the vector space, and this time maybe from the other side. So let's say we want to estimate this from above. This from, yeah. Yeah, we want to estimate this from below. So of delta. And how do we do that? Well, we don't look at the generating set, but we look at one generating set and then we just overestimate the set of relators. And it turns out that in this case, this is also rather easy to write down, fd of delta minus, and now it turns out that you have at least d plus 1 relation for every d minus 1 phase. And you get this. Okay, so these are two inequalities that you can get just rather easily from the definition of A of delta. And this now turns this inequality that was already quite nice into an even nicer inequality. Why? Well, now what I have to prove is that if I look at A of delta in degree D, and look at its dimension, and I look at A of delta in degree D plus 1, and look at its dimension, then I want to have this inequality. Right? It should be larger in degree D than it is in degree D plus 1. We can do a sanity check. So maybe we don't know how to do this for delta, but for sigma, certainly we know to prove something like that. I claim that if we look at A of sigma, then this inequality is true. In fact, we have an isomorphism in degree D in degree D plus 1. Why is that?
The duality?
Yeah, that's just the duality. Yeah, that's just the duality, that's right. So now, there's something that comes to the rescue. And this statement, what comes to the rescue, at least partially, is the Hartlefshed theorem. So if the Hartlefshed theorem, what is the Hartlefshed theorem? In this case, well, the Hartlefshed theorem would say that if I look at this ring A of sigma in degree k, and A of sigma in degree 2d plus 1 minus k, then this isomorphism of vector spaces is really somehow supported inside the ring. So it's induced by a multiplication with a degree 1 element, but now I have to, okay, so I have to multiply, I have to take some power of this, 2d plus 1 minus k, so this is just minus 2k. Okay? So this is a Hart-Lefschetz property. Right? We saw this also yesterday. Problem is, we don't know how to prove this. Right? Problem, don't know this in general. But if sigma is the boundary of a polytope, then this is actually something that this we can just look up in an algebraic geometry book. Then we really just have the Hart-Lefschetz theorem for, let's say quasi-smooth projective varieties. And we're only looking at the toric picture here. And then, okay, so how does this help us? Well, how does it give us anything? Well, if this is indeed true, if we have the Hart-Lefschetz property, then in particular we have an isomorphism from the degree d component to the degree d plus 1 component. Induced by the multiplication. And now what we have, right, we have this surjection onto AD of delta. And we have the restriction of that surjection. Okay, but now this is an isomorphism if we have the Hart-Lefschetz property. In particular, this map here must be a surjection as well, which gives us this inequality. Okay? Well, but this only works if sigma is particularly nice, but most spheres are not nice, not somehow the boundary of polytopes. In particular, if you cannot embed this delta in a way that somehow on each face it is linear, right, then you don't have a chance to realize it as the boundary of a polytope. Whatever the...
In the case of polytope, that L is the sum of monomials corresponding to edges, is that right?
You can choose it that way, yeah. That's one, yeah.
And you cannot do that in general, or can you?
You cannot do that in general.
It's a fact.
All right. That's okay. So we will discuss this a little later. So in general, we just don't have this. We don't have this nice geometry coming from complex algebraic geometry. So there's something missing that we have to fill in some other way. So how do we prove this inequality without using the Hart-Lefschetz theorem?
In Stanley's proof, did he use, was this all he used?
He used the Hart-Lefschetz theorem, yeah. I mean, he wasn't interested in this conjecture, but he was interested in the G conjecture. But he used the Hart-Lefschetz theorem. This is how he was able to prove the G conjecture for polytopes, exactly. So,
yeah, how Lefschetz is wrong, is false, or is it, or you just don't know it?
we will get to that. Okay, we will get to that.
You're going to learn everything today.
Not everything, but we will learn something, I hope. So how else would we prove this inequality? Well, there's another way that's kind of nice, and this was kind of the whole inspiration that started this whole project. It's what you do is, okay, so let's look at an ideal. Okay, A of sigma surjects onto A of delta, and then there's an ideal here, I delta sigma. Okay, this is just defined as the kernel of this map. Okay, and in fact, it's just, if you think about it, these are just the monomial ideal, right, generated by the non-faces of delta in A of sigma. Okay, so now what do we know? Well, we have this perfect pairing, AD of sigma, times AD plus 1 of sigma. All right, it goes to the reals. And now what we can do as well is we can look at this ideal here, right? This ideal in degree d and this ideal in degree d plus 1. And we can restrict this pairing to this ideal. All right, so this here is a subspace here, and this here is a subspace here. And okay, so now what property of this pairing would imply this inequality, well, we want it to be non-degenerate at least on one side. So this is somehow what I call the bias-Poincare duality. Okay, if this pairing is non-degenerate on the left. Okay.
Like the rank of the matrix is the number of rows. Is that what that means?
Yeah, exactly. So in particular, this would give us this inequality, right? And it kind of, I mean, it makes sense that this should be true in some way or form, right? But so I mean, if you expect an ideal to become larger in higher dimensions, you kind of expect that somehow if you choose its ideal generically, then this should be true. And it's more this. There's a geometric idea here that you could try to make solid, right? So if you, what do you want? Well, you want to show that for every x here, there exists an element y here, such that x times y is non-trivial. Clearly, there exists an element y prime here, right? There exists y prime in AD plus 1 of sigma, right? This is just Poincare duality such that x times y prime is not equal to 0, right? So you have these two objects, whatever they are, right? We don't really have any algebraic intuition or any algebraic geometry intuition any longer. But if we had, then what we are trying to do now is to say that so we have our object x, right? It's some algebraic cycle, and then we have our object y prime. And now what we want to do is we want to push y prime into this ideal in such a way that this intersection number just doesn't change, right? Right. So we want to push this into some. Right, to push this away from some torus orbits, if you want, if you want to think about this on a geometric level. And what could you do? Well, you could try to prove this. You could try to push this along some Lefschetz pencil. So this should be somehow an indication that the Lefschetz theorem has something to do with that. But what does it have to do with that? So how do we realize this? And it turns out that it's not really good to try to realize this algebraically, to realize this geometrically, but it is somehow, it's easier to realize this on an algebraic level, on a purely algebraic level. And it turns out that this property, first of all, is not always satisfied, even if sigma is nice, even if sigma is a smooth, even if sigma is a smooth toric variety, like the one nice example that I always make in this context is if it's just a project, the product of some projective lines. So this property, it turns out it's not true always, and there's a reason for that. So let me draw the polytope corresponding to the fan rather, corresponding to this the product of two projective lines, and more or less, right? So okay, so it should be somehow the subdivision of Rn into orthons, and it's more or less at this point. And now let's say, okay, this is my sigma, this is my sphere, and now you could take a subcomplex delta like this one here, and you could ask whether in this case indeed it is true that I delta sigma satisfies this bias Poincare duality. And it turns out that the answer is no in this case. And you can verify this by showing, okay, the ideal in this case, so this is delta, these two vertices. And the ideal I delta sigma is generated by this vertex and by this vertex. And they square to 0. Okay? Each of them squares with itself to 0, and they clearly don't multiply with each other. Okay, this is an issue. But it turns out that the failure has to do with the fact that if I restrict the linear system to these two vertices, and it does not act well as a Lefschetz element on this sphere, right? This delta is again a sphere, and in general I can think of it as a submanifold of codimension 1. And the Lefschetz, the linear system that I chose does not act well enough in terms of Lefschetz theorems on this codimension 1 sphere. And that's exactly the failure. But what this means is that if I know that somehow I can find a realization of delta that satisfies the Lefschetz theorem, then in particular I can force this ideal to satisfy this bias Poincare duality with respect to some other system of linear forms. Okay, so what I have to do now is choose different system of linear forms theta, and then this will be true for delta. And now I can do this for any subcomplex, right? It's a finite number of subcomplexes. And then I can ensure that for all subcomplexes, I delta sigma will satisfy this bias Poincare duality. So let me just sum this up. In the following sentence, or the following diagram. Right, so hard Lefschetz in lower dimensions, right, in codimension 1, implies that sigma satisfies bias Poincare duality with respect to a generic. Okay, so now there's something coming in. With respect to a generic theta for all delta subcomplex of sigma. Okay, so this is a kind of different thing. So what we saw is we saw these kind of Hodge-Riemann relations. Right? They say something about the index of the of this bilinear form. And what I'm saying instead is, okay, so I can force, if I know how to prove the hard Lefschetz in lower dimensions, then I can force something else. I can force them to be non-degenerate on many, many subspaces.
You just take like a random linear combination?
Yeah, once you know this, you can just take a random linear combination. But, I mean, it doesn't work for any, that's the point. Okay, it's not for any, but for a random one. For an open dense set of linear combinations of linear forms, this is true. Okay? So this is somehow the first part. And now you can actually already prove this Grünbaum-Kaleisa-Carrier conjecture for manifolds of dimension, for complexes, for two complexes that you embed into R4. Because you only have to understand the hard Lefschetz for lower dimensions. And then you get this pairing statement for four-dimensional spheres. But for lower dimensions, well, it turns out that it reduces to the hard Lefschetz on two-dimensional spheres, but every two-dimensional sphere is the boundary of a polytope. Okay? And then you know the Lefschetz theorem just because, okay, so because every boundary of a polytope again satisfies, for complex algebraic reasons, the hard Lefschetz theorem. So then, okay, so you have this statement. Now, I mean, if you want to continue this kind of induction, if you want to prove the higher dimensional version of these conjectures, then you're in some way, you're stuck, right? You prove that you have this bias Poincare duality, but how do you get back to the hard Lefschetz in the same dimension? Well, what you can do is inspired by another theorem that is kind of, it's a very basic combinatorial theorem that probably everyone learns in the first course on discrete mathematics, and this is a Hall marriage theorem. What does a Hall marriage theorem state? Well, it states that if you have two finite sets, x and y, and you have an expanding relation between them, so a relation between them, let's call it R, such that for all the subsets A of x, the cardinality of A and the cardinality of the acceptable partners of A in Y satisfies this inequality. All right, so there are more acceptable partners than your chosen set. Then the conclusion is that there exists a matching between x and y. They're supported by this relation. In particular, in other words, there exists an injective morphism from x to y that somehow is supported on this relation. All right, this is okay. So this is and this is in essence what we want to do. All right, because we already know the expanding relation. Okay. But we want to prove that, okay, so what we want to prove is exactly this isomorphism from AD to AD plus 1. All right, this we want. But we have the expanding relation. So we want a kind of an algebraic version of the whole marriage theorem. And now it turns out that this is kind of tricky to get in general. But it turns out that you can make this work by using not only this expanding relation, but also the fact that not only some of the dimensions grow, but by the fact that you know that you can control the pairing on every subspace. Okay, so in fact, so there is a kind of whole marriage theorem that goes like this. Okay, so now the hard Lefschetz for these spheres. Okay, so now I chose the parameters differently for 2D plus 1 spheres. Okay? And now I only discussed this middle hard Lefschetz theorem for you, but it turns out that you can do this in general for all the hard Lefschetz.
What is the expansion is a generalization?
Huh?
What is the expansion is a generalization?
This is not the expansion of somehow spectral expansion. It's just somehow this dimension expansion, right? Somehow that an ideal grows from one degree to another.
So it's a dimension.
Right, so what we proved earlier, right, assuming hard Lefschetz in lower dimension, or somehow what I somehow sketched in a very, very sketchy way, is that the dimension of ID and this ideal in degree d plus 1 grows. All right, this we got from the pairing. And I'm saying that if you use not only this, but the pairing, the fact that the pairing is non-degenerate on the left, then you actually get back the hard Lefschetz theorem.
You have to choose your linear forms generically. You never have to change them again. I mean, only for
so you don't have to change them again. But I mean, of course, you have to. I mean, this linear form you have to prescribe. So yeah.
Would you say philosophically that hard Lefschetz it's kind of a generalization of Hall's theorem?
Yeah, kind of, yeah.
Yeah. By the way, I'm familiar. There is like operator version of Hall's.
Okay, I would love to.
Maybe it's kind of.
I would love to hear them. Yeah. I mean, the kind of what is the underlying lemma here? You construct this L here. How do you do this? And it's a kind of embarrassingly simple linear algebra lemma that you use. It's
By the way, that selector is the analog of that selector in Hall's theorem. You picking up a partner. What is that?
Yeah, this is okay. So we'll describe this now. Okay, so how do you construct this map? Well, I mean, there are distinguished linear maps that you kind of know how to control, and these are just the prime divisors. These are just correspond to the variables or just to the vertices of your simplicial complex. Okay, these are the maps that you control. They are not good from a perspective of a Lefschetz type theorem, right? They will never give you the Lefschetz theorem unless you have a very special kind of polytope. But you control them in a good enough way. They correspond to your selectors. And now, how do you combine them? You want to take a generic linear combination, and the lemma that you use is the following. So you have A and B, and these are two maps of infinite of vector spaces, V to W. Okay, these are two linear maps. They're finite dimensional, but somehow the vector spaces have to be vector spaces over some infinite field. That's my condition. Okay, so V and these are over infinite fields.
Simultaneously trigonalizable.
And then, what you want to describe, right? You want to, in some way, you have A plus epsilon B, right? A plus epsilon B, and you want to say that this this generic linear combination of A and B, it should be as good as possible. So one thing that you could ask for is that the kernel of A plus epsilon B is the intersection of the kernel of A and the kernel of B. Okay? How do you get this? Well, I mean, in general, this is hard to do in general. But now what you do is a kind of the selector from Holt's theorem. And this is that, okay, so it's a kind of natural condition. You take B times applied to the kernel of A. All right? And you intersect it with the image of A. Right? And what do you want, right? So this should map B should map to whatever you haven't married yet. So the intersection should be empty. All right? And that's it. So this is basically what you call the selector.
Yeah.
Right? It's a very simple lemma. You just have to.
Actually, you always can kind of simultaneously triangleize them.
Yeah.
2, not for 3.
Yeah, it only works for 2. Unfortunately, I always have to make this work only for 2, right? I have one that's I always want to marry more, right? But it only works for 2.
And there are fundamental actually issues here, but anyway.
Huh?
There are some fundamental issues why it works for 2 or not.
Oh, okay. I always try to do this for more maps. I wanted to always find a homological way to do this for all maps at once and to not find an inductive. But okay, so if you're saying that there's no hope to do that, then I would love to hear why. Okay, good. Anyway, so this is the theorem that is the lemma that is used to construct this map. Why is it kind of perfect why is it kind of perfectly suited to what you want to do? Well, it turns out, so the kernel of A and the image of A as subspaces of the ring that we started with are orthogonal complements. And this is a pullback. So what you're saying is that the kernel and somehow the orthogonal complements should not have an intersection. But orthogonal complements do not have an intersection if the pairing on them is non-degenerate. And that's it. Somehow this is how it comes in. And now, okay, so now you have to use this in somehow. There are some technical issues that you have to overcome, but this is kind of the underlying idea. I don't know how much time I have left, actually, but 5 minutes? Okay, good. Then let me open for questions. I mean, we already started, but.
So in this selection construction, actually your goal was to make the kernel as small as possible?
Yeah. I mean, if you do this, right, so you do this iteratively, right? Always another map, another selector until some of the kernel is empty.
But anyway, so this question, if you're given a bunch of matrices, you want to take linear combination.
Yeah.
You would like to make a kernel as small as possible.
Yeah.
It's identity testing, and it's a hard thing.
For
2 it works because 2 magically have some properties.
Okay, I would love to hear about the magic property. Yeah.
Is there an algebraic statement of what you're doing? In other words, in the end, you're just working with these rings, these commutative algebra with some structure coming from combinatorics.
Yeah.
And then you're proving some hard Lefschetz theorem under some properties.
Yeah. Well, I mean, the hard Lefschetz theorem. So essentially, somehow there are 2 kind of properties, right? So what I'm saying is that you have the hard Lefschetz theorem in the end for these kind of spheres, but you have something that I call the Hall-Laman relations that replaces the Hodge-Riemann relations. And this just states, okay, so the Lefschetz theorem induces a bilinear form, right? It induces a quadratic form. And usually it says something, the Hodge-Riemann relations say something about the signature of this bilinear form, provided your Lefschetz theorem is.
I'm trying to understand what it is from the topology of this PL map that you really used in this algebra. Very little, it seems. I mean, of course.
Yeah, I mean, what it uses in a very strong way is this fact that okay, so if you do a pullback to a vertex, and the link of a vertex is again a sphere, and you have this global Poincaré pairing. Okay, these are 2 structures that I use. Yeah, otherwise it's very different from kind of the classical proofs of the hard Lefschetz theorem. Yeah. Okay. More questions?
So what are you saying about the Hodge-Riemann thing? So you're saying Hard-Lefschetz gives Hodge-Riemann naturally? But
No. So then in the classical case, Hard-Lefschetz gives you this. This Hard-Lefschetz comes in tandem with the Hodge-Riemann relations, right? And the Hodge-Riemann relations say something about the signature. What I'm saying is not about the signature, but I'm saying that this bilinear form, if you're restricted to very natural subspaces, and these are exactly the subspaces coming from subcomplexes, then your bilinear form is non-degenerate. It's a kind of non-trivial thing, right? In general, you expect that somehow there will be subspaces where somehow whether the bilinear form will be isotropic, right? The quadratic form will be isotropic. But I'm saying on very nice subspaces it will be anisotropic. This is more useful for me in the end to make this induction work. Okay. Yeah, I would love to discuss that. Okay, thanks.